This lecture looks at summaries used for simple linear regression. It is in Module 3, comparing two or more continuous variables. Previously, our numerical summaries have included things like means, medians, standard deviations, and ranges, and our graphical summaries have included histograms, mean plots, and box plots. However, these summaries do not describe relationships between continuous variables. They provide information about groups and a continuous variable. Remember that our explanatory variable is the variable similar to the cause in a cause and effect relationship. It is used to try to explain the differences in the other variable. The response variable is similar to the effect in a cause and effect relationship. It is the variable trying to be explained by the explanatory variable. Let's look at the summaries in the context of study example 1. We are looking at the relationship between tap water consumption and hemoglobin change, so our two variables are tap water consumption and hemoglobin change. The graphical summary we will use is a scatter plot, which is a plot of a two-variable relationship. The explanatory variable, which is the amount of tap water consumed, is placed on the x-axis, while the response variable, which is hemoglobin change, is placed on the y-axis. Each point represents the measurement of the subject on variable 1 and variable 2, and the resulting plot of all pairs is a scatter plot. Variable 1 is the explanatory variable, while variable 2 is the response variable. Upon creation of a scatter plot, we inspect its form, direction, and strength. If the form is linear, the data look to be in a straight line. The form may also be curved, which occurs when the data tend to follow a parabola shape or another curved pattern. If the form is random, it means that a trend line cannot be fit to the data, and the points do not form any sort of pattern. If the association is positive, then as one variable increases, the other also increases. That is, the direction is up and to the right. If the association is negative, then as one variable increases, the other variable decreases. That is, the direction is down and to the right. If there is no association, there is neither a positive nor a negative direction to the trend. Strength measures how closely data points adhere to this imaginary trend line. This may be weak, moderate, or strong. Looking at the scatter plot, we see that tap water consumption, the explanatory variable, is positioned on the x-axis, while hemoglobin change, the response variable, is positioned on the y-axis. Take a few minutes and decide what you think the form, direction, and strength of the scatter plot are. Please pause this video while you make this determination. The form is approximately linear, and the direction is positive or up and to the right. However, it can be difficult to determine strength based solely on the scatter plot. Therefore, for linear relationships, we have a different way of describing the strength of a relationship. Correlation quantifies the linear relationship between two variables. It is key to note that correlation only holds for linear relationships. If there's curvature, then correlation will not make sense. Correlation ranges between -1 and 1 inclusive. This means that correlation can take the values of -1 and any value in between. The sign of the correlation represents if the association is negative or positive, while the number represents the strength. Values close to -1 and +1 represent the strongest negative linear relationships and the strongest positive linear relationships, respectively. A value of 0 signifies no linear relationship. Values closer to 0 represent weak linear relationships, while values close to -1 and 1 represent strong linear relationships. Correlation is a numerical summary, just like a mean or a standard deviation. In our sample, correlation is signified by R, while the parameter for the population is represented by the Greek letter rho. This image shows some examples of positive and negative perfect, strong, and moderate correlations. In real data, you will almost never see perfect correlation. We can use Excel to find the correlation between two variables. The Excel command is correl, and it takes two arguments, which correspond to the raw data for the two variables. In this case, the correlation between tap water consumption and hemoglobin change is 0.4957. This is very close to 0.5, so the correlation between the two variables is of moderate strength. We can see this when we draw the trend line. The points are clustered fairly closely to the line, but there is still some distance between the furthest points and the line. It is important to note that correlation does not imply causation. Just because two things are related does not mean that one causes the other. The correlation provides evidence for cause and effect, but it is not the only piece of evidence needed for such a determination. In fact, there's even a website devoted to looking at silly examples of things that are correlated but do not have a cause and effect relationship. This is one such graph. The trend line we sketched on the scatter plot can be formally found and used to model the linear relationship between the two variables. Just like with lines you found in algebra, this line will have both a slope and a y-intercept. The simple linear regression model is shown on the screen. This model should look similar to y equals mx plus b. However, we have an error term because this is a statistical model and we need to account for random error. This is what's happening in the population, and we use our line to estimate that. B0 represents the y-intercept, and beta 1 represents the slope of the line. Just like with our previous tests, we have assumptions that need to be met to use this model. The first is that subjects are independent, while the second is that the errors come from a normal distribution that has a mean of 0 and a constant variance. There are ways to check these assumptions, which will be covered in the next lecture. The best line to fit the data is determined by minimizing the errors, specifically the sum of the square of the errors. The errors are found by calculating the straight line distance from each point to the line, and then the errors are squared so that they're all positive. That way, positive and negative error values don't cancel each other out. The line with the smallest sum of the square of the errors will fit the data the best and is often called the line of best fit. This is the line of best fit shown on the scatter plot from the earlier slide. Excel will calculate this for you. In addition, the formula for the line is shown. We call the formula for the line the prediction equation, since it predicts what is happening in the population. It is the estimated linear regression model, or the line of best fit. It has a slope and a y-intercept. Just like in algebra, the y-intercept tells the value of y when x is 0, and the slope measures the change in y for each 1 unit change in x. We call this line the prediction equation because it can be used to predict responses, which we denote by y hat. This means that if we have how much tap water a woman drank, we can estimate her change in hemoglobin. However, we must be careful not to extrapolate. This means that the prediction equation is only valid for the range of data you use to create it. Looking back at our scatter plot, we see that our x values range from around 100 to around 600. Therefore, if the woman drank less than 100 liters or more than 600 liters of tap water, we cannot accurately predict her hemoglobin change based on our model, as we only use the range of values from 100 to 600 liters to create the model. Otherwise, we could end up with some odd results. Let's look at study example 2. We are looking at the relationship between PHR use and diabetes quality measures, specifically HbA1c. In Concept Practice 9, you will create the scatter plot and calculate the correlation and prediction equation for the relationship between PHR use and HbA1c using data from study example 2.